Thank you for taking the time to watch this short video. Over the next few minutes, you will see how Cadence's FPGA System Planner can significantly reduce your FPGA-based system design cycles. FPGA System Planner applies I/O synthesis technology to automatically create FPGA pin assignments that are optimized for both the FPGA and the PCB. We will begin with a brief overview of FPGA System Planner's unique, patented approach to the FPGA pin assignment process and how FPGA System Planner, or FSP, fits into the design flow. We'll then move into a quick demo of FSP in action. Cadence is uniquely addressing a growing problem in FPGA-based system design. Old design tools and methodologies are inadequate in addressing the design needs of today's complex FPGA-based systems. FPGA System Planner shortens the time and effort needed for optimum initial pin assignment, accelerating PCB design schedules. FSP speeds the integration of FPGAs with the OrCAD PCB design creation environment. FSP eliminates unnecessary, frustrating design iterations during the PCB layout process. FSP eliminates wasted physical prototype iterations caused by configuration pin mistakes, general FPGA pin assignment errors, and incorrect voltage connections. FSP accommodates changes late in the design cycle far more easily than conventional methodologies. Using FSP in your design process will improve your team's productivity and quality of results. ROI studies show that FSP can pay for itself in the first project. Now that you've had the overview, let's take a look at FPGA System Planner in action. This is the FSP user interface. The area at the top right is the canvas and is where the FSP system level design will be captured. At the bottom is a transcript window, and to the left is a library window from which the components used in the design will be selected. To begin, I'm going to place a Vertex 5 LX330T device. To do that, I simply drag the FPGA from the library window onto the canvas. This FPGA, as with all FPGA devices in FSP, is an intelligent model that not only understands the complete I/O usage rules for the pins on the device, but is also tightly linked with FSP's I/O synthesis engine. Next, I'll place a TI DSP and a DDR2 DIMM on the canvas. Because Xilinx recommends placing DDR memories on the left or right of the FPGA, I'll rotate and move the DDR and zoom in on the working area a little more. It appears that I am creating the start of an initial PCB layout, and that is indeed the case. The placement of the components on the board has a direct effect on which pins of the FPGA should be used to create connectivity that is optimized for both the FPGA and the PCB. Defining the connectivity intent between the DSP, the DDR2, and the FPGA is a matter of simply selecting the DSP and DDR2 and telling FSP which group of signals should be connected to the FPGA. This raises the level of abstraction and removes the need for the designer to focus on each pin of the FPGA. Once the connectivity intent is defined, the I/O assignments can be established using FSP's patented I/O synthesis engine. As you can see, the connections, which are DRC accurate, were created very quickly. FSP has, in real time, synthesized a set of FPGA pin assignments which simultaneously meet the needs of both the FPGA designer and the PCB designer. The ability for FSP to wire up the design so rapidly allows designers to explore the architectural trade-offs both with regards to device selection and component placement. For example, the DSP can be easily rotated and its FPGA connections resynthesized. To do this with existing techniques would require hours of rework and close communication across the entire design team. Now that the connections have been established, the next step is to forward the design to the FPGA, schematic, and PCB designers. Using pull-down menus and a set of simple forms, FSP can automatically generate the symbols and schematics and a PCB placement script. FSP allows the designer to either generate custom symbols or use schematic symbols from an existing corporate library. Once the symbols have been created or selected, the schematics can be generated. FSP can also generate a PCB placement script which, when executed, will automatically open Allegro and place the components on the PCB in the same physical locations as on the FSP canvas. Finally, the FPGA constraints files can be generated and passed to the FPGA designer. Once the system-level design has been captured in FSP, the I/O pins synthesized, and the symbol and schematic generation process is completed, the design can be opened in OrCAD. These schematics are maintained and updated by FSP as the design matures. At this point, the design can be packaged and opened in the Allegro PCB editor. The component placement you see here was automatically established by running the script generated in FSP. This ensures that the FSP canvas and PCB placement locations are closely linked. Integration between Allegro and FSP allow the PCB designer to make placement changes as well as pin swap requests. Swap requests can be made for multiple pins or for 2 pins at a time. Those swap requests are then fed back to FSP for validation and execution. Using FSP to validate and perform the actual pin swaps ensures that the FPGA DRCs are adhered to and that the FPGA design will continue to operate correctly. Please contact your local Cadence or Cadence channel partner for more information or to arrange a demonstration of OrCAD FPGA System Planner. To find the Cadence representative nearest you, please visit cadence.com. Thank you for your time.